Hi, so now we're going to learn about how we learn by changing our brain. So I love this idea about your brain actually changing itself into a new state, or in a way a new brain, so that it's now able to better overcome a challenge. I think it's extremely exciting and a little bit creepy, but I hope you will also be interested to find out more about how and why it does this. So what is learning, this time from a neuroscience point of view? So learning is the change to neural circuits in response to experiences, and uh, often the changes happen so that you can enable a change in some future behavior. And this often involves changes to the strength of the synapses, which are the connections between different neurons. So to begin with, let's step back and ask, from the brain's point of view, what is an experience or an event? So in the brain, these events or experiences are coded as patterns of neural activity. And a pattern of neural activity is just the set of neurons that are active at nearly the same time. So here we see a lovely video from Jim DiCarlo at MIT, who's done some pioneering work comparing artificial intelligence networks with the brain. What they show here, in each layer of the network, is a set of different units, each unit corresponding to a neuron, with a color if the neuron is active and grey if the neuron is inactive. What you see is that the pictures going into the system, into the eye, change, and this corresponds to a change in the activity that proceeds up through this hierarchy of layers of the deep neural network, which corresponds to a hierarchy of cortical areas in the brain, so that each image has its own corresponding pattern of neural activity. So we're going to start, like in the previous lecture, speaking about sensory memory, and this is in the visual system also known as iconic memory. And you can see, for example, if I showed you an image of this zebra, there'd be a very brief period where you see a kind of a shadow or decaying version of the image. Peter Rossum's group in the Netherlands have shown that the amount of time with which you can retrieve an iconic memory corresponds quite nicely to the amount of time that activity dies off in neurons in V1, which is the primary visual cortex, or the first step of visual processing in the cortex. And this lasts for about 100 milliseconds, give or take. So neural activity corresponding to sensory memory is brief, and it's actually restricted primarily to sensory parts of the cortex, and it doesn't propagate more deeply along the hierarchy of visual processing more deeply into the brain. We have a simulation of this type of activity. Here we can see brain activity spreading from the primary visual cortex, the back of the brain, taking a few steps deeper into the brain, but it does not reach the prefrontal cortex or most of the other associated parts of the brain. You can also see that activity dies out very quickly, on the order of about 200 milliseconds. So after sensory memory, we get into working memory activity. Working memory activity, again, in the visual case, can start from primary visual cortex, or V1. It again propagates in, but it propagates far deeper into the brain, shown here in the red regions. And working memory activity in these red regions at the top can actually resist distracting information coming in the meantime, and hold its pattern for several tens of seconds. These are results from a simulation from a recent biologically defined neural network model that we developed. And here we see comparison between our model simulation results and experimental data from over 90 experimental studies. The areas shown in turquoise are those that show activity that persists for many seconds, and the areas shown in gold are those that show very brief or transient activity. And this, you can see that there's an extremely good match between the pattern of persistent activity in the model and that we see in the experimental data. So neural activity corresponding to working memory propagates deeply into the brain, and the pattern of neural activity largely persists after the sensory memory has died. And this can even persist through other distracting sensory information in the interim. However, activity in the early sensory areas often dies off, and this can correspond psychologically to a loss of the fine sensory detail when you're maintaining something in your mind. If you want to learn about how different parts of the brain represent different types of information at different levels of detail, see a future lecture on deep architectures in the brain. But this pattern of activity where you see this transient activity in sensory areas and activity that persists for longer in other parts of the brain that are deeper in the brain, like the prefrontal cortex, it begs the question, why can some areas maintain their patterns of neural activity better than others? And this is something that we're going to cover in more detail in our video on recurrent architectures. What are the consequences of this deeper processing for memory? Well, we see that a greater depth of processing means that information travels further into the brain and up the brain's hierarchy. This means that it's processed by more regions along the line of the cortical hierarchy. And information is therefore sustained for longer, and we see that neurons actually remain coactive or active at the same time for longer periods. And this is critical for something called Hebbian plasticity. And Hebbian plasticity is really the foundation of learning in the brain, and it's often remembered by this simple phrase that neurons that fire together wire together. So the idea is that when one neuron frequently contributes to activating another neuron, their synaptic strength will increase, whereas if that same neuron fires but does not lead to activity in another neuron, that connection will become a bit weaker. Here we can see the general mathematical formulation of Hebbian plasticity, where the rate of change in the synaptic weights from the presynaptic neuron to the postsynaptic neuron is a function, h in this case, of the presynaptic activity and the postsynaptic activity. And in the literature there are different versions of this function h. But this Hebbian rule seems to form a basis for associating different things in a single memory. So how do we actually go about encoding some memories from working memory into our long-term memory? It's clear that not everything that we have in our working memory gets transferred to long-term storage. So for example, if you already watched the cognitive science version of how we learn, do you still remember the one-time code from the video? If you do, it'll be quite impressive. I think I certainly forgot it, and I think most people will have. So then, why is that the case? Why did you forget that and remember other things about your day? So, in particular, from a neuroscience point of view, what enables some working memories to be marked for encoding into long-term memory? Here we're going to introduce a key third player in plasticity, and this third player is called neuromodulation or neuromodulators. So a neuromodulator is a chemical that's released in the brain that changes or modulates how two other neurons communicate at the synapse. So neuromodulators are things like dopamine and acetylcholine and serotonin. They signal things like reward and importance to the brain. And they form the basis of a three-factor learning rule, which basically says that by adding dopamine or acetylcholine or serotonin to Hebbian plasticity, you can essentially mark that as a potential important thing to encode in long-term memory. It's a little bit like putting your name on the list of the long-term memory club, which should increase your chances of getting in. So here essentially is what mathematically the three-factor learning rule might look like. So it's very similar to the Hebbian learning rule, but now we have this extra factor G, which is the neuromodulator. So the rate of change now in the synaptic weights from the presynaptic neuron to the postsynaptic neuron depends on a neuromodulator G and a function of the presynaptic firing and postsynaptic activity. Like all brain chemicals, neuromodulators act on neurons and connections by binding to receptors, and that works a lot like a key fitting in a lock. A particular neuromodulator will only bind to its own receptors. And we actually found that these locks that neuromodulators can bind to, or the receptors, are much more prevalent deep in the cortical hierarchy, so in the prefrontal cortex and parietal cortex, than in early sensory parts of the brain, like V1. So this suggests that there's much more capacity for modulation and perhaps for learning in these types of areas that contribute to higher cognitive functions than in the areas that are responsible for encoding sensory information. So now we're going to switch our focus more to long-term memory. And we're going to talk first about retrieval and then work back to encoding. So please take 1 minute to recall in as much detail as you can a recent experience. And you can choose it yourself. It can be something from today or something from the last few days. And you can please write this down to try to get as much detail as you can. So continue the exercise as I'm speaking to you. And now we're going to talk a little bit about what's happening in your brain as you're trying to recall all of the details of this recent event. So what's happening is that your brain, when you're trying to retrieve that information, is trying to recreate the pattern of neural activity that you experienced during the original event. So when you're ready, come back to the video and finish the exercise. And here again we see a really nice video from Jim DiCarlo showing the patterns of neural activity that change when the images coming into the eye change. However, when you're trying to remember or retrieve that information, there's no information coming into the eye that's relevant to the memory. And in fact, you're getting a signal from within the brain, perhaps higher up in the brain, like the hippocampus or the prefrontal cortex. And these structures send messages to try and initiate a kind of a recreation of the original neural activity pattern. And if that's successful, it will lead to you experiencing something like the original event again. However, we all know that memory is not perfect, so it's very unusual or perhaps impossible to perfectly recreate an event in memory. Although some people, for example with post-traumatic stress disorder, may get more intense and accurate memories than most other people. So what happens here when you're trying to reconstruct a memory is that you're trying to start from an initial partial or incomplete pattern, something that reminds you of something that happened, and then what you want to do is try to complete the pattern and reconstruct the entire memory. For example, if you play the start of a song that you recognize, very often your brain will try to continue the next pieces of the song and complete that pattern. You can let me know on Teams whether or not you recognize that song. The hippocampus, and in particular part of the hippocampus called CA3, is the area that's most famously involved in this function, and it's thought to be particularly good at completing patterns because of a strong recurrent structure to how the neurons in that area are connected to each other anatomically. However, some version of pattern completion likely occurs throughout the cortex and perhaps many other parts of the brain, and this seems to be essential in order for you to recreate a pattern of activity that you're experiencing all across your cortex. So now we're going to speak briefly about a classic model of pattern completion for memory retrieval. So those of you who've taken computational neuroscience in third year, you will have come across this before. So we're just going to go across it again and revise it briefly. So the Hopfield model is a very early neural network model from 1982 that was very influential. It's got a fully connected set of neurons or units, and these units are connected by symmetric weights. So the strength of the connection from one neuron to another is the same as the connection in the opposite direction. The neurons or units in this network only output binary outputs. They use a +1 or a -1 here. So the dynamics of the model work as follows. At each time step, the neuron I is active with a +1 if the weighted sum of all of the other neural activities, weighted by the synaptic inputs to this neuron, if they are above a threshold, theta. And if it's below that threshold, the neuron becomes inactive, which is coded by a -1. This is an energy-based system whereby the network seeks to reach a state of minimum energy, which corresponds to an attractor state of the system. So here we can see the energy function, and activity will continue to evolve with these dynamics until it reaches a local minimum of this energy function E, which is an attractor state. This network is able to store multiple patterns, and it does this by essentially following Hebb's law, which we just encountered. And if you want to embed multiple patterns P into this network, this is how you should do it. And let's talk briefly, because it might not be completely obvious, why this follows Hebb's law. So this basically says that if for a pattern A, both neurons I and J are active, or both inactive, then the synaptic weight should increase and decrease otherwise. But if the network has seen a whole collection of different patterns, and we call this collection P, then the synaptic weights between neurons I and J should reflect the fraction of patterns for which the neurons are coactive. So essentially, if the neurons fire together across many of the patterns, they will wire together or have a particularly strong connection together. In contrast, if they don't fire together in most of the patterns, then the connection will be weak. So this is just Hebb's law. So now we're going to finish off today's video talking again about consolidating, this time from a neuroscience point of view. Consolidating memories often occurs during sleep, and this is really a process of strengthening, generalizing, and adapting memories so that they can be used in certain ways. During sleep, neurons in the hippocampus replay activity that played out during the day, but they play it much faster than what happens during the actual experience. And this activity from the hippocampus, which is shown here in blue, spreads to the cortex, shown here in red. However, over time, this could occur over days, weeks, or even months. The representation of the memory seems to sometimes move completely from the hippocampus to the cortex, so that this memory will no longer be lost, for example, if the hippocampus is damaged. However, there's also a theory in the literature that this transfer of a memory from the hippocampus to being completely cortical might coincide with a difference in the nature of the memory, and it starts becoming less episodic and more semantic. So it's like you may have had the experience where sometimes if you know some event happened in your life, after some time it no longer feels that when you remember that you're really retrieving the precise details of the memory, and it becomes a bit more fact-like, where you just remember the main ideas. So this is called systems consolidation, and it's related to episodic and semantic memory. But there's also a type of consolidation of skills or procedural memories that occurs during sleep, and this is related to automatizing the skills and freeing up cortical processing power. So with expertise, certain skills, such as reading, come to activate less of the cortex over time. This coincides with when they become more automatic and your expertise increases. So this is a slightly unusual map of the brain. This is a scan of the brain of a child who's starting to learn to read. And here we can see what's called a flat map of the cortex. So they've basically opened up virtually on a computer, not in real life. They've opened up the brain of the child, and they've flattened it out, onto a page so that you can see the entire parts of the cortex, even the bits that are folded in normally and hard to see. But the child is, of course, okay, this was all just done on a computer. So what you can see is that these are days before school has started, and they've got this child to try to read, although it wasn't able to read yet. We see very little activation of the cortex. However, after 2 months in school, the child is starting to be able to read, but with a lot of conscious effort, and you see a lot of cortical activation. These are orange parts on this map here, and you can see that many different parts of the brain are activated, and this continues throughout the school year as they continue to improve. But when they were scanned again about over 2 years after beginning training to read, you can see that now when they read, only a very small and selective part of the cortex is activated during reading. So you can see that with expertise, skills and procedural memories start taking up less of the cortical space and can start to become performed automatically. With this, you start to see an increasing reliance of these expert automatic skills on areas that are deeper in the brain, such as one that's involved in habits, a brain area called the basal ganglia, which is actually a collection of lots of little brain areas. Functionally, this frees up our cortical processing to consciously tackle challenging problems. For example, once you've learned to ride a bike, you no longer really need to think about riding the bike. And although you should probably think about where you're going, it's also possible to think about other things while you're going for a nice, quiet cycle. And to recap today, we learned that experiences are represented in the brain as patterns of neural activity. Sensory memory neural activity patterns are restricted to the outer sensory areas of the brain, and they fade quickly on the order of about 100 milliseconds. Working memory activity spreads deep into the cortical hierarchy, so from the back of the brain right up to the front, the prefrontal cortex, and these memories and the activity is maintained for tens of seconds. Working memories themselves then may fade after tens of seconds, or they could be encoded into long-term memory through Hebbian plasticity. And encoding into long-term memory doesn't automatically happen, but it's more likely to happen if a neuromodulator like dopamine, acetylcholine, or serotonin is also released at the same time. So memory retrieval is the brain's attempt to reconstruct a pattern of activity that arose during the original event. And we went briefly over a classic model called the Hopfield model, which simulates this process. And we learned that consolidation of memory during sleep can strengthen, generalize, or automatize a memory. And we learned about how that may correspond to changes in the anatomy of where this memory is stored. So thank you very much for listening, and if you're still curious and want to find out more, then there are a lot of additional references here, and I suggest choosing the one that seems the most interesting for you right now. And in the next videos we're going to learn about deep hierarchical architectures in neural networks and the brain.